China Micius Quantum Communications, History, Present and Future. Introduction. The Micius satellite, named after the ancient Chinese philosopher Mozi, stands as a landmark achievement in the field of quantum communications. Launched on August 16, 2016, it became the world's first quantum communications satellite, marking a significant milestone in the evolution of secure communication technologies. This report delves into the historical context, technological advancements, current achievements, and future prospects of the Micius satellite in quantum communication in China and globally. Historical context. Initiation of the Micius project. The journey of Micius began in 2011 when the Chinese Academy of Sciences (CAS) collaborated with the Institute for Quantum Optics and Quantum Information (ICOQI) of the Austrian Academy of Sciences. The primary goal was to explore the potential of quantum communication and develop a satellite capable of transmitting quantum information securely. 2011 – Collaborative efforts between CAS and ICOQI commence. 2012 – The mission objectives and technical research goals are finalized. 2013 – Development milestones are reached, including authorization of prototype instruments and environmental testing of the satellite structure. July 2016 – Micius is transported to the Jiuquan Satellite Launch Center for pre-launch preparations. Launch and specifications. The Micius satellite was successfully launched aboard a Long March 2D rocket from the Jiuquan Satellite Launch Center. Weighing approximately 600 kilograms and costing about $100 million. Micius is equipped with advanced technology designed for quantum key distribution (QKD) and quantum entanglement experiments. Launch date: August 16, 2016. Launch vehicle: Long March 2D. Mass: 600 kilograms. Estimated investment: $100 million. Quantum technology and innovations. Quantum entanglement and secure communication. At the heart of Micius's capabilities lies the phenomenon of quantum entanglement, where pairs of photons are generated in such a way that the properties of one photon instantaneously affect the other regardless of the distance separating them. This property is crucial for secure communication protocols, enabling the development of unbreakable encryption methods. Micius facilitates quantum key distribution by sending pairs of entangled photons to ground stations. The first successful long-range secure communication occurred in 2017 when quantum keys were distributed between Beijing and Vienna, showcasing a distance of 7,400 kilometers. Achievements and breakthroughs. Micius has made several groundbreaking contributions to the field of quantum communications. First secure communication, in 2017. Micius achieved the first successful quantum key distribution between two ground stations located 7,400 kilometers apart. Direct links without trust. Recent developments allowed ground stations 1,200 kilometers apart to establish secure communication links without needing to trust the satellite, further enhancing security protocols. Global impact. The satellite has sparked interest in quantum communication technologies worldwide, highlighting China's leading role in this emerging field. Current status and applications. Functionality and missions. Micius operates in a sun-synchronous orbit at an altitude of approximately 600 kilometers, enabling it to provide quantum communication capabilities to various ground stations across China and Europe. The satellite has been instrumental in establishing secure communication frameworks that are resistant to eavesdropping and hacking attempts. Current missions include transcontinental quantum key distribution, ongoing projects to establish secure links between various international ground stations. Research collaborations with numerous global institutions to explore the applications of quantum cryptography in various fields. Political and strategic implications. The development of Micius is not merely a scientific endeavor but is also intertwined with geopolitical considerations. Following the revelations of widespread surveillance by Western governments, particularly the disclosures by Edward Snowden in 2013, China accelerated its efforts in quantum cryptography to enhance its national security and ensure secure communications. The satellite's capabilities have positioned China as a leader in quantum technology, prompting other nations to explore similar initiatives, thereby fueling a global quantum race. The implications of this technology extend beyond communications, potentially impacting military and strategic operations. Future prospects: expansion of quantum communication networks. Building on the success of Micius, China plans to expand its quantum communication infrastructure with the upcoming Micius 2 and Micius 3 satellites. The objective is to establish a comprehensive global quantum communication network by 2030. Quantum Internet vision: the long-term goal is to create a global quantum internet that offers unparalleled security features powered by the principles of quantum mechanics. International collaborations: future missions may involve collaborations with international partners to enhance capabilities and establish a robust quantum communication ecosystem. Challenges and considerations. While the advancements in quantum communication are promising, several challenges remain. Technological limitations: the current technology is still in its infancy and further research is needed to overcome existing limitations related to distance data transmission rates and integration with existing communication infrastructures. Regulatory frameworks: the establishment of international standards and regulations governing quantum communications will be crucial to ensure interoperability and security. Conclusion: the Micius quantum communications satellite has redefined the landscape of secure communications, demonstrating the potential of quantum technologies to revolutionize information security. As China continues to lead in this field, the implications of Micius extend beyond technological advancements to encompass strategic, political, and economic dimensions on a global scale. The future of quantum communications holds great promise, with the potential to reshape how nations communicate securely, ultimately contributing to the development of a safer and more secure global communication network. The development and deployment of China's Micius quantum communications satellite represents a pivotal moment in the history of quantum technology, with implications that extend far beyond mere scientific achievement. Here are some counterintuitive aspects of this narrative. 1. Perception of security. While Micius is touted as the first hack-proof satellite, the notion of being entirely secure in communication is complex. The satellite does not transmit messages itself, rather it facilitates the distribution of quantum keys that can be used for secure communication. This means that while the keys are theoretically secure, the systems and protocols that utilize these keys are still vulnerable to various forms of attack. Thus, the perception of absolute security can be misleading. 2. Global competition versus collaboration. The Micius mission highlights a paradox in international relations. Although it has sparked a competitive environment, particularly between China and Western nations, it has also led to collaborative scientific efforts, as seen in the partnership with the Austrian Academy of Sciences. The dual nature of competition and collaboration in quantum technology creates a complex landscape where nations both strive to outpace one another and simultaneously seek shared advancements. 3. Historical context. The launch of Micius has been likened to the launch of Sputnik, marking the beginning of a new race, not just in space but in the domain of communication security. This comparison is counterintuitive because while Sputnik initiated a space race driven by competition, Micius could lead to a new era of global communication standards that may necessitate cooperation to develop universally accepted protocols and systems. 4. Political motivations and technological innovation. Interestingly, the push for quantum communication technology in China can be traced back to the revelations of mass surveillance by Edward Snowden. This implies that technological innovation in quantum communication is not driven solely by a desire for advancement but is also a response to geopolitical pressures and concerns about privacy. The emergence of Micius as a strategic asset underscores how political context can shape technological trajectories. 5. Trust in technology. The foundation of quantum communication relies heavily on the principles of quantum mechanics, particularly entanglement. However, the dependence on Micius as a facilitator of secure communication introduces a paradox regarding trust. While the technology may be secure in theory, the trust placed in the satellite itself as a resource raises questions about the reliability of the systems that leverage its capabilities. The notion that parties can communicate securely without having to trust the satellite challenges conventional understandings of trust in technology. 6. Future of communication. The ambition to establish a global quantum internet by 2030 reflects a profound shift in how we conceptualize communication. This vision challenges the current infrastructure dominated by classical methods and raises questions about digital sovereignty, data ownership, and the potential for new forms of digital divide. The transition to a quantum internet may not solely enhance security, it could also exacerbate existing inequalities if access to this technology is not equitably distributed. 7. Role of non-state actors. While Micius represents state-driven efforts in the quantum race, it is essential to consider the role of non-state actors such as private companies and academic institutions. Their participation in quantum research and development can lead to innovations that challenge or complement state efforts, suggesting a more decentralized future in quantum communications than the current narrative of state control implies. In conclusion, the Micius quantum communications satellite serves as a symbol of technological advancement, yet its implications are layered and complex. The interplay of security, trust, competition, and collaboration in the context of quantum communications invites a re-examination of fundamental assumptions about technology governance and international relations. As nations navigate this new landscape, the outcomes may prove to be as unpredictable as the quantum phenomena that underpin this groundbreaking technology. Overlooked content and its significance in the Micius Quantum Communication Report. The report on China's Micius quantum communications satellite QUSS presents a wealth of information on its historical significance, technological achievements, and future implications. However, certain aspects of the report are likely to be overlooked by many readers, yet these elements are critical for understanding the broader implications of quantum communication technology, particularly in the context of global security, international relations, and technological competition. Below are key overlooked points and their significance. 1. Historical context and strategic necessity. One of the most overlooked points is the historical context surrounding the Micius satellite's development, particularly its connection to the revelations by Edward Snowden in 2013 regarding widespread internet surveillance by Western governments. This event catalyzed China's urgency to develop quantum communication technologies. The report mentions that this incident prompted a significant boost in Chinese research into quantum cryptography as a response to perceived vulnerabilities in traditional communication methods. Significance. This historical backdrop illustrates the geopolitical motivations behind technological advancements. It frames Micius not merely as a scientific achievement but as a strategic initiative driven by national security concerns. The push for quantum communication can be viewed as a direct response to the loss of trust in existing communication infrastructures, thus highlighting the intersection of technology and international power dynamics. 2. The nature of quantum security. The report emphasizes Micius as the first hack-proof satellite. Yet many readers may not fully grasp the implications of quantum key distribution (QKD) and entanglement-based cryptography. The ability to establish secure communication links without relying on the trustworthiness of the satellite itself is a profound breakthrough. The satellite merely serves as a source of entangled photon pairs which can be used to generate secure keys for communication between ground stations. Significance. This point is significant because it challenges traditional notions of trust in communication systems. In classical systems, trust is often placed in the intermediary, e.g., a server or a router. In contrast, quantum systems allow for a new paradigm where security is inherently tied to the laws of quantum mechanics. This shift could revolutionize not just military communications but also sensitive sectors such as finance and healthcare, where data integrity and privacy are paramount. 3. International collaboration versus competition. While the report discusses international collaborations, particularly between Chinese and Austrian institutions, it also hints at a competitive landscape emerging from quantum technologies. The ability of Micius to facilitate secure communications has implications that extend beyond mere scientific inquiry. It positions China as a leader in a potentially transformative field that could redefine international relations. Significance: this duality of collaboration and competition is essential for understanding the future of global technology governance. As nations invest in their own quantum communication capabilities, the potential for a quantum arms race emerges. Countries may seek to secure their own communication infrastructures independently, leading to fragmentation in global communication standards and protocols. This competition could drive innovation but also exacerbate geopolitical tensions. 4. Future implications for global Internet infrastructure. The report outlines plans for future Micius satellites and the vision of a global quantum Internet by 2030. However, the technological, regulatory, and infrastructural challenges that accompany this ambition are not sufficiently explored. For instance, the transition from classical to quantum communication networks would require significant advances in technology, including the development of compatible ground infrastructure and international agreements on standards. Significance: the realization of a global quantum internet could fundamentally alter how data is transmitted, stored, and secured across borders. It raises questions about regulatory frameworks, data sovereignty, and the role of governments in overseeing such critical infrastructure. As nations strive to build their own quantum networks, issues relating to interoperability, security standards, and equitable access to technology will become increasingly pressing. 5. Ethical considerations in quantum communications. The report does not delve into the ethical implications of quantum communication technologies, particularly in terms of surveillance and privacy. While quantum communication is posited as a secure method to protect sensitive information, the same technologies could potentially be used for advanced surveillance capabilities that compromise individual privacy. Significance: this oversight is crucial as it invites a broader discourse on the ethical responsibilities that accompany technological advancements. As quantum technologies become more integrated into communication systems, societies must grapple with the implications of their use, balancing security with the preservation of civil liberties. This dialogue is essential for shaping policies that govern the use of quantum technologies in a manner that respects human rights. 6. Interdisciplinary collaboration. The collaboration between physicists, engineers, computer scientists, and policymakers in the development of Micius is implicit in the report but not explicitly highlighted. The success of such an ambitious project relies not only on technical expertise but also on the integration of diverse fields of knowledge and perspectives. Significance: recognizing the interdisciplinary nature of quantum communication development underscores the importance of fostering collaborative environments that bring together various fields. This collaboration is essential for addressing complex challenges that arise in the integration of new technologies into existing systems and ensuring that innovations serve the public good. 7. Public perception and understanding of quantum technologies. Lastly, the report lacks a discussion on public perception of quantum technologies and the necessity for public education regarding their implications. As quantum communication technologies advance, public understanding will play a crucial role in shaping policy and fostering acceptance of these technologies in society. Significance: educating the public about quantum communication can demystify the technology and promote informed discourse around its applications and implications. Public engagement is vital for democratically navigating the challenges posed by emerging technologies, including issues of security, privacy, and societal impact. Conclusion. The report on China's Micius quantum communications satellite encapsulates groundbreaking advancements in the field of quantum communication, yet it also presents numerous layers of significance that are easy to overlook. Understanding the historical context, the nature of quantum security, the implications for global infrastructure, ethical considerations, and the importance of interdisciplinary collaboration and public perception can provide a more comprehensive view of the Micius satellite's impact. As quantum technologies continue to evolve, these factors will play a critical role in shaping their trajectory and the future of global communication systems. 1. Historical significance of Micius satellite. The Micius satellite represents a monumental advancement in quantum communication technology as the world's first quantum communications satellite. Launched in 2016, it showcases China's leadership in the field of quantum technology. The satellite, named after the ancient Chinese philosopher Mozi, has established long-distance secure communication links that were previously unattainable. The timeline of its development, beginning with the collaboration between the Chinese Academy of Sciences and the Austrian Academy of Sciences in 2011, underscores the strategic importance placed on quantum communications by China. 2. Quantum entanglement and security. Central to the operations of the Micius satellite is the phenomenon of quantum entanglement, which allows for the generation and distribution of quantum keys essential for secure communication. Micius successfully demonstrated quantum key distribution (QKD) over a distance of 7,400 kilometers between Beijing and Vienna, illustrating its ability to create unhackable communication channels. This use of entangled photons ensures that any attempt at eavesdropping can be easily detected, thereby safeguarding the integrity of the transmitted information. The implications of this technology extend beyond mere encryption. They represent a fundamental shift in how secure communication can be achieved. 3. International cooperation and competition. The development and success of the Micius satellite have stimulated both international collaboration and competition in the field of quantum communication. While it has fostered partnerships, particularly between China and Austria, it has also intensified the global race for quantum supremacy. The satellite's achievements, such as the establishment of secure communication links and the potential for a future global quantum internet, have prompted other nations, including the United States, Russia, and various European countries, to accelerate their own quantum research initiatives. This competitive landscape raises significant geopolitical considerations and reflects the strategic importance of quantum technologies. 4. Future prospects in global quantum internet. Looking ahead, the success of Micius lays the groundwork for the future development of a global quantum internet. Plans for subsequent satellites like Micius 2 and Micius 3 aim to expand quantum communication networks and ultimately establish a secure worldwide quantum communication infrastructure by 2030. This initiative not only aims to enhance communication security but also to redefine the global landscape of information technology and cybersecurity. As countries recognize the military and political implications of quantum communication, the establishment of a quantum internet could become a crucial factor in international relations and national security strategies. 1. Sputnik and the space race. 1957. The launch of Sputnik 1 by the Soviet Union on October 4, 1957, marked the dawn of the space age and catalyzed the space race between the United States and the USSR. This event not only demonstrated the technological prowess of the Soviet Union but also raised concerns over national security and the potential for space-based military applications. The launch of Sputnik led to significant investments in science and technology in the U.S., including the establishment of NASA and the acceleration of research in various fields, ultimately reshaping global geopolitics and the perception of space exploration. 2. Enigma machine and World War II cryptography. The German Enigma machine, used during World War II for encrypting military communications, represents a pivotal moment in the history of cryptography. The efforts to break the Enigma code, primarily by British mathematician Alan Turing and his team at Bletchley Park, not only showcased the importance of cryptography in warfare but also laid the groundwork for modern computing. The successful decryption of Enigma messages provided the Allies with critical intelligence, significantly impacting the outcome of the war and demonstrating the strategic importance of secure communications. 3. The Manhattan Project 1942–1946. The Manhattan Project was a research and development project during World War II that produced the first nuclear weapons. This historical case illustrates the intersection of science, military strategy, and international relations. The project not only advanced scientific understanding of nuclear physics but also had profound implications for global power dynamics and security concerns in the post-war world. The secrecy surrounding the project emphasized the importance of secure communication and information sharing among scientists and military officials, as it sought to prevent enemy nations from gaining knowledge of nuclear capabilities. The successful development of atomic bombs ultimately reshaped global politics and initiated the nuclear age. Future outlook: predictions for quantum communications in China and beyond. The launch of China's Micius quantum communications satellite in 2016 marked a pivotal moment in the history of telecommunications, setting the stage for a new era of secure communication technologies. Given the rapid advancements in quantum technologies and the geopolitical landscape, we can anticipate several key developments in quantum communication over the next decade and beyond. 1. Expansion of quantum communication networks. By 2030, China aims to establish a comprehensive global quantum communication network utilizing not only Micius but also subsequent satellites like Micius 2 and Micius 3. These satellites are expected to enhance the capabilities of quantum key distribution (QKD) and entanglement-based communication, resulting in a robust network that connects major cities and strategic locations worldwide. The proliferation of ground stations across Europe and Asia will facilitate this expansion, fostering international collaboration in quantum technology. 2. Integration with classical communication systems. The future of quantum communication will involve seamless integration with existing classical communication systems. As quantum technologies mature, hybrid systems that leverage both quantum and classical methods will become prevalent. This integration will provide enhanced security for global communications, especially critical infrastructures such as banking, government communications, and military operations. The ability to manage and switch between quantum and classical channels will be crucial for operational flexibility and security. 3. Advancements in quantum encryption techniques. As quantum communication technologies evolve, we can expect significant advancements in quantum encryption methods. Techniques like entanglement swapping, quantum repeaters, and advanced error correction will improve the reliability and range of quantum communication. By the late 2020s, these enhancements could enable practical long-distance quantum communication between continents, effectively overcoming current limitations imposed by distance and atmospheric interference. 4. Increased international competition and collaboration. The success of Micius has sparked interest from other nations, leading to an international race in quantum technology development. Countries such as the United States, European Union members, and emerging powers like India and Russia are investing heavily in their quantum communication initiatives. This competition will drive innovation but may also lead to geopolitical tensions as nations seek to secure their communication networks against potential espionage. Collaborative efforts, particularly in research and development, will be essential to address common challenges and establish global standards for quantum communication protocols. 5. Quantum Internet development. The ultimate goal of quantum communication is the establishment of a quantum internet, a network that uses quantum signals for communication, offering unparalleled security against eavesdropping. By the late 2030s, we may witness the first operational quantum internet testbeds enabling secure communication for a range of applications, including secure banking, confidential diplomatic communications, and private data transfers. The implications for privacy and data security could be transformative, fundamentally changing how sensitive information is shared. 6. Economic implications and new business models. As quantum communication technologies mature, new business models will emerge focusing on providing quantum-secure communication services to businesses and governments. Companies specializing in quantum encryption and secure communication solutions are likely to proliferate, creating a new sector within the tech industry. This shift will attract significant investment and talent, further accelerating the development of quantum technologies. 7. Addressing ethical and regulatory challenges. With the rise of quantum communication technologies, ethical and regulatory challenges will become increasingly prominent. Issues related to data privacy, surveillance, and the potential for misuse of quantum technologies for malicious purposes will require careful consideration. Policymakers will need to establish frameworks that ensure responsible use of quantum communication while promoting innovation. International agreements may also be necessary to regulate the use of quantum technologies across borders. 8. Quantum communication in space. As interest in space exploration grows, quantum communication technologies will likely play a crucial role in interplanetary communication. Future missions to Mars and beyond may leverage quantum communication for secure and reliable data transmission between Earth and spacecraft. This capability will be essential for ensuring the security of sensitive mission data and communication with astronauts. Conclusion. The Micius satellite has set a remarkable precedent in the field of quantum communications, with its implications extending far beyond its initial achievements. The future of quantum communication, particularly in the context of China's ambitions, is poised for significant growth and transformation. As nations compete and collaborate in this emerging field, the development of secure, efficient, and reliable quantum communication networks will redefine global communication standards, addressing security concerns and enabling new possibilities for data transmission. The next decade will be critical for realizing the full potential of quantum communication technologies, shaping the future landscape of telecommunications.